Welcome to this video that I'm going to use to go through an entire curve sketch just so you can see the process that is used. And I've selected one that has rational and a rational expression to start, because when it has a rational expression that will require us to also do asymptotes. If it's a polynomial function, we don't have to worry about asymptotes. Alright, so I'm going to start to finish, go through the curve sketch, put all my information together, and then draw what I believe this graph should end up looking like. So I'm going to start with intercepts. So intercepts are found by taking your original function and determining what would make it equal to 0. What would make y equal 0, which is your f of x, and then find your y-intercepts by substituting 0 for your x. So here we go, intercepts. Pen on the go here. So intercepts. Let's go x-intercepts first. So the x-intercepts are found by filling in 0 for the y. So f of x is the same as y, so it's 0 equals 8 onto x minus 2, and that'll be over x squared. The only way that a fraction, rational expression, can equal 0 is if the numerator is equal to 0. So when you're trying to figure out what would make this fraction equal to 0, you really just have to examine the numerator and say, well, what would I have to fill in here for x to make it equal to 0? The only x value would be 2. So that tells me there is an x-intercept at 2 and 0. Now, don't look at the denominator. Sometimes students say, well, what about x equals 0? The problem with x equals 0 is it makes this function not 0, but undefined, which is not what I'm looking for. All right, on to your y-intercepts. So the y-intercepts are found by making the x equal to 0. So 8, 0 minus 2. This time we're getting a 0 in the bottom. Regardless of what happened up here, it doesn't make any difference. We're going to get negative 16 over 0. You're not allowed to have 0 in the denominator, so that means this is impossible, which means this graph has no y-x-intercepts. Asymptotes. So asymptotes, let's suppose I start with vertical. So vertical asymptotes are found by identifying any x values that will make the original expression equal to 0, which means set the denominator equal to 0. So in this one, the denominator is just x squared. Well, that would only ever become 0 if x equals 0. So this is the equation of your vertical asymptote, x equals 0. Your horizontal asymptote is found by taking the original expression, expanding out the numerator and the denominator, so it has to be in completely expanded form, and then find the limit as x is approaching positive and negative infinity. And we have a process that allowed us to do that, and it was dividing everything by the highest power of x that you see anywhere in the rational expression. So once I do that, hopefully your knowledge of limits and limits at infinity will tell you that this one is going to equal 8 over x, which is still going to be going to 0. 16 over a really big number squared is going to go to 0. Or x squared over x squared is going to give you 1. Now this is fine. You can have 0 in the numerator over 1. That just tells me then that my answer is 0, which tells me that the horizontal asymptote is going to be the line y equals 0. So this x equals 0 is actually the y-axis, and y equals 0 is the x-axis. So in this graph, the x and y-axis are going to serve as vertical and horizontal asymptotes. On we go. So we've looked at intercepts, we've looked at asymptotes. Now we're on to increase and decrease, which will also then pair up and let us find local extrema. So we're going to get these two next. They're found using the first derivative. So increase, decrease. The first thing you need to identify are the critical values of the first derivative. So that would be anything that makes the derivative. F prime of x, here's the derivative. Now this one was presented in a nice factored form for us, so it's negative 8 multiplied by x subtract 4 divided by x cubed. So any number that makes this equal to 0 or undefined. So essentially what you end up doing is you set the numerator equal to 0 if it's a fraction. So in this case that'd be negative 8 times x minus 4. And you want to figure out what x value would actually make this equal to 0. Well, it would have to be a 4. So there's one critical value. That would make the numerator 0. Then you say, well, what would make this undefined? Well, it would be undefined if the denominator was 0. X cubed equals 0, x equals 0. Now I'm kind of maybe going overboard with what I'm showing in terms of work here. You really should have been able to look at this and by inspection say 4 and 0 are your critical values, because 4 makes it 0 on the top, 0 makes it 0 on the bottom. You don't necessarily have to show this workout. But for my video explanation here, I figured I would do that. Alright, so now you're going to set up intervals. Negative infinity to the first critical value, and then 0 to 4, and then 4 to infinity. Across the top, you list the factors of your derivative. So negative 8 is one of the factors. X subtract 4 is another factor. X cubed is another factor. These three in a quotient will tell me what the first derivative is in terms of positive or negative, and then that will tell me something about the function. Oops. Let's erase this. Tidy it up a little bit. So turn this into a grid. Alright, so now you're going to identify, if you pick a number from this interval, how it will impact this factor, and this factor in regards to its sign. Well, the number negative 8 could never be anything but a negative. Some negative number, take away 4, your answer will always be a negative. A number between 0 and 4, so take 2 for example, and you subtract 4, that's going to also be negative. Now this is a number that's more than 4, so 20 minus 4, you're going to always get positive answers. A negative number cubed, you should get a negative result. A positive number cubed, you should get a positive value. A positive number cubed, you should get a positive. The derivative is the quotient of 3 negatives. So if you divide and multiply a combination of 3 negatives, your answer should be negative. And that means that the original function is decreasing in that interval. From 0 to 4, my derivative is, let me see, 2 negatives and 1 positive, multiplied or divided, a combination of the two. That would have to give me a positive result, which means my function is increasing. 2 positives and 1 negative, that gives me a negative, so my function is decreasing. Now, relative extrema refers to local max and mins, so let's look at those, see if there are any. Local max, local min. Alright, so a local max is defined as an ordered pair on the graph where it switches from increase to decrease at a number that exists. So that's important when you have rational expressions, because sometimes what can happen is they'll switch decrease to increase or increase to decrease, but it'll switch at an asymptote line, a vertical asymptote. Alright, let's see what happened here. So I went decrease to increase, so think about it, if you were decreasing and switched to increasing, right? Decreasing on the left, increasing on the right, that's a local min. I should draw that, sorry. Oops. A local min is a decrease to increase switch, local min. Decrease to increase happened at 0. Now technically you're supposed to take this number, substitute it in the original function here to get your y value. Well, unfortunately filling in 0, it goes undefined. Now you do not write 0, undefined. That means that there is no point. That means that there is no local minimum. So you actually identify that you've checked and you realize what I was looking for, but because the function didn't exist there, there is not going to be a local min. Local max is when you switch from increase to decrease. Local max. Increase to decrease happened at the number 4, which is a defined value. I would take the number 4, substitute it in here for the x, and 4 minus 2 is 2, times 8 is 16. over 4 squared, which is 16, so it's going to come out to be 1. 4 comma 1 is a local maximum. So that's 2 more items. So all my increase decrease is now looked after. I figured out any local extrema. That takes me down to where's the graph concave up and down, and any inflection points that may exist. Alright, so that's all found. Essentially doing the same thing I just did here, except using the second derivative. So my concavity check, I need the critical values of the second derivative. Criticals. So f double prime at x is equal to, let's go up and check on that one, 16 onto x minus 6 over x to the 4th. So this one I'm just going to do by inspection and say that this fraction would equal 0 if x was 6, and it will go undefined if x was 0. So those would be the 2 critical values. Sign table, negative infinity to 0. It's a bad 0, but that's a 0. 0 to 6, and then 6 to infinity. Across the top, you're going to list your factors. 16, x subtract 6, x to the exponent 4. That'll tell me whether my second derivative is positive or negative, which will then tell me whether my function's concave up or concave down. Alright, the number 16 could be nothing but positive. Pick a number between negative infinity and 0, which is any negative number, and subtract 6, your result's going to be negative. A number between 0 and 6, pick 3 as an example, minus 6, you're going to get a negative. A number that's more than 6, let's say 10, take away 6, the result's going to be positive. This one, because regardless of what you put in here, you're going to raise it to an even exponent, whether it's positive or negative, it makes no difference. Your result is always going to be a positive number. 2 positives and a negative in a quotient will give you a negative result. If it's negative, our concavity is down. 2 positives and a negative again will give you another negative result, concave down. 6 to infinity, that's 3 positives in a quotient. That will give me a positive. That's concave up. So we did have one switch in concavity, and it happened at the number 6. So you can see it's 6, it went down to up. Now, much like relative extrema, you have to be careful that it's not switching at a vertical asymptote, because it can also switch at a vertical asymptote. So if you have that happen, make sure you don't call it an inflection point. It has to be an actual point on the graph that exists in order for us to classify it as an inflection point. Okay, so the only inflection point was when x was 6. I need the y value when x is 6. 6 take away 2 is 4 times 8 is 32 for my numerator. 6 squared is 36. These will both divide by 4, so it's actually 8/9. So pretty well 1, but a little bit less than 1. So 8/9 would be my inflection point. Okay, so this is the part where most students, when they're going to run into problems, it's going to be taking all of these clues that they've just uncovered and now helping them use these clues to draw a graph of what they think this looks like. Alright, so I've got an ordered pair 6 and 8/9, so I need my x scale to go to 6. My y scale doesn't need to be very much because the highest I ever go is up to 1, I guess. I did have an x-intercept at 2 and 0. So let's see. I'm going to cross here. So now that you've identified, so I don't really need much here. 1, 2, I'm just going to go up to 2. Remember I said this one I got to go over to at least 6. So 1, 2, 3, 4, 5, 6. So there's 6, 7, a couple extras. 8. -1, -2, -3. Wasn't really much going on over there. nor down here. I should have, sorry, that scale's not very good. Whatever scale you used here has to be about the same down here, so let's just put -1 there. All right, so here's what you do. Start with ordered pairs. Go down the list. So intercepts. What do we get for intercepts? We just got the one x-intercept at 2 and 0. And we got no y-intercepts. So that's a clearly defined point that we found on the graph. Go to local extrema. So local extrema, we had a local max at 4, 1. 4 and 1. The only other ordered pair we uncovered was an inflection point at 6, 8/9. 6. So 8/9 is just slightly lower than 1. Right? 8 over 9 is less than 1. So it's a little bit lower than that point. All right, next thing, put any asymptote you found. So we found a vertical asymptote of x equals 0. So you're going to put a dotted line right down through, now I'd be putting this right through my axis. There's x equals 0. Notice that one goes right through top to bottom. Horizontal asymptote is just identifying what the graph's doing as x goes to infinity and what's happening when x goes to negative infinity. So here, we're just going to put dotted lines out at the end. So this was y equals 0, and then out at the left end. And as I told you, we're only going to examine ones where it's the same at both ends. A bit more complicated ones, they could in fact be different, but we will not run into those here in Pre-Calc 12b. Now, what we have to rely upon, now at this point, especially when you're just getting started with these, what I often recommend you do lightly with pencil is, so with your asymptote lines, your graph is going to get closer and closer to, but not touch that line. The problem is we don't know whether it's here or here. So what I suggest you do is lightly put little arrows with little lines with arrows on them, just getting closer and closer to that line. Do the same at the other end. And you're going to, again, they got to be done lightly because you're going to erase one of these. You only use one or the other. On a vertical one, you'll either use up here or down here. Not sure which one. Up here or down here. Your sign table will tell you which of these you're going to use and which one you're going to erase. Okay, so on we go to our sign table. Increase, decrease, it has to kind of jive with your concavity. So it's saying from negative infinity to 0, this function should decrease, which tells me there's no way I'm up here. Because if I was up here, this has got to be moving slightly away from the asymptote, which would have to send it up this way. So I have to be down here in order to be decreasing. Well, if I'm here and there's no critical values in here, all that's going to happen then is I'm going to decrease, 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 and hook onto this arrow right here. So I'm going to try and do this with a smooth curve as best I can. So that'll roll down, and that would keep going because this line just goes forever down this way. And that would be from negative infinity to 0. Now I didn't check my concavity chart, but based on what happened here and what has to happen, hopefully our chart is saying concave down in that interval, and it does, which makes sense. All right, next interval is 0 to 4, and my graph should be increasing, and my graph should stay concave down all the way to 6, actually. So from 0 over to x is 6. So how's that going to happen? Well, in order for this function to increase, it's going to have to be down here coming up this way. So that tells me that, let's backtrack for a second. So I didn't use this one, and because I'm going here, that would mean I'm not using this one up here. Now we're trying to determine whether we're here or here. Well, if I was here, the graph would have to come this way, which would be decreasing. So that can't be the one I'm going to use. So I'm going to erase that one, and I'm going to go down to the bottom, and I'm going to be using this one. So I'm going to be increasing, right? Increasing. Now then I've got to cut through these points properly. So it's going to increase through the x-intercept. There's my highest point, my local max. It's going to turn around and start to come back down. Now in terms of concavity, it's rolling concave down like a hill. Hill, hill, hill. This is a point where it's going to switch. Now you say, well, it switched. Why did it switch? Well, it switched so that it would turn out and then act like an asymptote going out this way. It's going to get closer and closer to this line but not touch it. So I kind of have this mapped out now. I'm going to come up through here, rounding down, Then slightly change it so that it's curving the other way. Your tangents go underneath, concave up, and head out here. All right, so you try and do that with one smooth sweep if you can. Here I go. Not easy to do on these drawing tablets, but I'll do the best I can. So I'm going to come up through my intercept, slightly rolling down, still rolling down, down, down. Now, wasn't bad, but this had to be the highest point. It looks like these are about the same height. I should have headed downward a little bit more. Just fix this. So I should have kind of rolled down. All right, so concave. So I knew I was using here, which I erased up there. Increasing, concave down. Now it switches to concave up, so it's going to be rolling slightly the other way and head out towards our asymptote line this way. And there's what we would suggest that this would look like. So of course what you could do is on Desmos now, if you didn't have an answer key, which of course on a test day you don't have this option, but if you're at home doing an assignment, you say, I don't know if I did this right or not. Let's just get our head wrapped around what the question was originally. So 8 onto x minus 2, I'm just going to write this down. 8 onto x minus 2 over x squared. So you're going to graph that original function and see what it ends up looking like. So I'm going to go to Desmos. So Desmos would be here. And I'm going to type in the original function, y equals 8 brackets, oh, that's 9. 8 brackets x subtract 2 divided by x squared. Let's see how we did. Well, this is what it looks like. If you want to just zoom it out a little bit, maybe. I'd say we did reasonably well. When you zoom in, we had it kind of zoomed in. We were just looking something like this. You can't see that was headed over there and down like ours did. This headed up and down towards the asymptote. And you get a better look at it if you zoom out. But I'd say that based on our hand-drawn sketch, we kind of captured the essence of that graph. All right, so that is an example of a complete curve sketch involving a rational expression. The only difference for a non-rational expression is that you do not have to worry about these. So a non-rational expression means there is no denominator here in the original function. So hopefully this helps with you putting together complete curve sketches. There's lots of practice there for you now as we prepare to do a summative assessment on this material in the coming days. Thanks for watching. If you have any questions or concerns, please reach out and I'll do what I can to help you out. Thank you.